The following is a tutorial on Bronsted acid-base theory. As you can see, a Bronsted acid is any molecule or ion that donates an H plus ion, which is a proton, in a reaction, typically an aqueous solution. A Bronsted base is an H plus or a proton or an H plus ion acceptor, be it a molecule or an ion, in a reaction. So for example, if you have ethanoic acid reacting with water to form ethanoate anion and hydronium ion, you can see based on the reactants and the products which reactant accepted a proton and which reactant donated a proton. In this case, if you notice the ethanoic acid, which has one extra H plus compared to ethanoate ion, must have been the H plus donor. So by virtue of that, the ethanoic acid is the Bronsted acid. So I'll call that acid 1. In each chemical reaction there will be two what we'll call conjugate pairs of Bronsted acids and bases. So the conjugate of ethanoic acid, the conjugate base, would be ethanoate, because ethanoate anion forms as a result of ethanoic acid donating the H plus to water. Since in this reaction water accepted an H plus ion or a proton from the ethanoic acid, mainly by virtue of one of the lone pairs on the oxygen of water attracting the H plus ion away from the ethanoic acid. So this covalent bond breaks and the H plus forms a covalent bond with the oxygen atom of water sharing the lone pair of electrons between the two nuclei. So because the water molecule accepted the proton, that is a Bronsted base. I'll label that base 2, because in accepting that H plus, the water became hydronium ion, and therefore it formed its conjugate acid. So I'll label that acid 2. The subscripts are meaningless. You can label acid Q and base Q, and acid X and base X. You're just using subscripts to denote the conjugate pairs. So it's pretty easy to figure out and label conjugate pairs. Just look at which substances or which species look alike. For example, the ethanoic acid looks just like ethanoate anion, except the ethanoic acid has one more H plus in the formula, and therefore the ethanoic acid is the conjugate acid of ethanoate, its conjugate base. By the same token, water looks like hydronium, except hydronium has one more H plus in the formula, so that makes it the conjugate acid to water's conjugate base in this reaction. There are plenty of other reactions in which water will act as a Bronsted acid, but this is just not one of them. A little comment on the degree to which a given acid will ionize water, basically by donating an H plus ion to the water molecule. You know that most acids are weak, meaning that at equilibrium a very low percentage of the acid molecules have donated an H plus to water and thereby ionized into their conjugate base. To what degree will that occur depends on two factors. One is the strength of the OH bond containing the acidic H. So the weaker that OH bond is, in other words, the less energy required to break that bond as a result of a collision, the greater the percent ionization will be of that acid, and the stronger that acid will be. In most cases, the OH bond is strong enough such that there's a relatively low percent ionization, and that's why we see most acids are weak. The second factor is the more polar the OH bond, the more the H in that bond is closer to being an H plus ion or a proton to begin with, because of the low charge density near the H in a very polar bond. So the more polar that OH bond, the greater the percent ionization of the acid, and therefore the stronger the acid. So though all OH bonds are polar, some are more polar than others based on the rest of the acid molecule. So in the case of ethanoic acid, at equilibrium there's generally, for most concentrations, about 3% ionization. Most of the ethanoic acid molecules are just that, they're molecules. They have not reacted with water, they have not ionized into ethanoate and hydronium cation. To figure out just how weak the OH bond is and how polar the OH bond is will be the subject of another tutorial. Okay, so to reiterate a very practical concern in figuring out Bronsted conjugate acid-base pairs, they look pretty much identical, so almost identical. The exception will be that the acid of the pair has one more H plus in the formula. So, if you look at dihydrogen phosphate anion and hydrogen sulfide anion, they will react together and form their respective conjugates. Hydrogen sulfide anion will turn into hydrosulfuric acid, H2S, and you can see the hydrogen sulfide anion has one less H plus, or the H2S has one more H plus, making it the conjugate acid of the pair to its conjugate base HS minus. For the dihydrogen phosphate anion, compared to the hydrogen phosphate anion, the dihydrogen phosphate anion has one more H plus, therefore it is the conjugate acid of its pair. So it's very easy to pair up conjugates in a given reaction. Just look for the pairs that look similar, see which member of the pair has one more H plus in the formula, and label that the conjugate acid of the pair. The one with one fewer H plus in the formula is the conjugate base of the pair. In this particular reaction, it seems that either of the reactants might have been the H plus donor. In order to see which does, you'd have to consult a table of strengths of these acids relatively, and that will determine which between the two is the stronger acid and will behave as such. Let's look at one more example. In this case we have ammonia reacting with water, and forming ammonium. I'll make the reverse arrow a little bit longer just to indicate that at equilibrium the reactants are favored based on just how weak this base is. So that forms ammonium and hydroxide. So you can see when ammonia is bubbled into water or reacts with water, the hydroxide concentration of the solution goes up, and that forms a basic solution. Ammonia solutions are basic. Alright, so what species look alike in this reaction? The ammonia looks like the ammonium. The ammonium has one more H plus in the formula than the ammonia, so this is the conjugate acid of ammonia, so they're paired up. For the water and the hydroxide, here you see that the water lost an H plus, it donated an H plus, so that by definition makes that a Bronsted acid. In donating the H plus here to the ammonia, sharing the lone pair of electrons on ammonia, and that's typically the source of the attraction to the H plus. As this bond breaks and the electrons stay with the oxygen, from that bond hydroxide is formed. So hydroxide is the result of water donating an H plus, making hydroxide the conjugate base of water, which in this reaction acts as an acid. So in this case water acted as an acid, whereas with ethanoic acid water acted as the base, So it really depends on what water is reacting with. Water is an example of an amphiprotic or an amphoteric, same exact meaning, substance. The prefix am means both or double. Someone who's ambidextrous can use both hands with equal dexterity or skill. So an amphiprotic or amphoteric substance can act as an H+ donor or acceptor depending on what that substance is reacting with. So water is an example of one. At the very least, any amphiprotic or amphoteric substance must be able to donate an H+, so it has to have at least an H in the formula, and in order to accept an H+, H+ would be repelled by a nucleus, but it's attracted to a lone pair of electrons, so amphiprotic substances must have at least one lone electron pair. In the case of water, water has two lone electron pairs by the oxygen atom. Let's do one last example from scratch, just identifying the Bronsted acid-base conjugate pairs in a reaction. This will be a reaction in aqueous solution between hydrogen carbonate anion. It's the most important anion that's carried in red blood cells, and the hydrogen sulfate anion. You can look in a table of values of strengths of acids, and you'll see that hydrogen sulfate is a much stronger acid than hydrogen carbonate. So between these two, the hydrogen sulfate will be acting as the proton donor. So as a result of that, hydrogen carbonate anion is going to accept an H+ and form carbonic acid. Without knowing which is the stronger acid, I couldn't make this prediction. And the other product, since the hydrogen sulfate is the stronger acid, it's going to donate the H+ and form sulfate anion. So, let's see what looks similar. Hydrogen sulfate anion and sulfate anion look similar. HSO4- is the proton donor, so that's conjugate acid, I don't know, I'll call it X this time, and it becomes its conjugate base, so it's base X. And the other two species look similar. The hydrogen carbonate accepted an H+ from HSO4-, so that makes it a base. We'll call that base Y. And in accepting the H+, it becomes carbonic acid. So there's the conjugate partner, acid Y. Now, which direction will be favored at equilibrium really depends on whether acid Y, the carbonic acid, is stronger or weaker than acid X, the hydrogen sulfate anion. I'd have to look that up, or you'd have to look that up in a table of acid strengths to determine that. So we can't answer that question right now. The question that we could answer, so I'll specify HSO4- hydrogen sulfate anion is a stronger acid than is hydrogen carbonate. So that at least enabled us to determine which is the Bronsted acid and the Bronsted base on the reactant side. Once that's determined, you could figure out what are the conjugate acid-base pairs. So we could just label that conjugate pair X and conjugate pair Y. So that is a basic skill required to continue in this acid-base equilibrium unit.